Welcome to this explainer. Today, we're going to completely shatter the myth of perfect materials. Usually when we hear the word imperfection, we instantly think of a mistake, right? Something broken or a flaw that desperately needs fixing. But in the fascinating world of materials science, an idealized solid with absolute, perfect atomic order simply does not exist. And honestly, thank goodness for that. Today, we're diving into how engineers and scientists actually rely on these flaws to manipulate the physical world and engineer the incredible materials we use every single day.
Here is our roadmap for today. We'll start with the power of imperfections, then zoom into point defects in crystals, explore impurities in solid solutions, lay down the rules of substitution, and finally, calculate material composition. Let's get right into it.
Section 1. The power of imperfections. We're kicking things off by totally reframing how you think about flaws in physical materials. Why on earth would you actually want a broken lattice structure? Well, think about a catalytic converter, the device in your car's exhaust system that cuts down on toxic pollutants. Those crucial pollution-reducing chemical reactions, they actually only happen because exhaust gas molecules physically latch onto deliberate surface defects on the metallic catalyst inside the converter. If those metallic crystals were flawlessly, perfectly smooth, the molecules just wouldn't catch, the reactions wouldn't happen, and the whole converter would be practically useless. The flaw is literally the entire mechanism for success here.
Here's another amazing example. The crucial takeaway here is that a quote-unquote perfect, pure metal is almost never what we actually want in real-world engineering. Take pure copper. It's beautiful, sure, but mechanically, it's actually really soft and pretty weak. You definitely couldn't build heavy-duty machinery out of it. But if you intentionally add what we call impurities, say mixing in about 30% zinc, bam, you've got brass. This new alloy is vastly superior. It's harder, it's stronger, and it's all because we deliberately crashed the pure copper party with foreign atoms.
Moving right along to Section 2, point defects in crystals.
Let's see how this builds by zooming way in to look at these imperfections on a microscopic atomic level. It is absolutely crucial to grasp this core definition. A crystalline defect is just a lattice irregularity that has one or more of its dimensions on the order of an atomic diameter. Basically, it's a tiny atom-sized hiccup in the pattern. And remember, an idealized solid with perfectly uniform order just doesn't exist in nature. Every single crystalline material out there is packed with these defects.
Now, there are two primary types of these microscopic hiccups, which we call point defects. First up, you've got a vacancy. This is exactly what it sounds like, a vacant lattice site where an atom normally sits, but, well, it's just missing. Think of a vacancy like an empty chair in a packed movie theater. Then you have the self-interstitial. This is an extra atom from the crystal itself that somehow got crowded into a void space that is normally unoccupied. Going back to our theater analogy, this is like someone awkwardly standing right in the middle of a narrow, crowded aisle.
When you visualize these structures side by side, the contrast is pretty wild. On one hand, you have the vacancy, a glaring empty spot in the neat rows of atoms, or the self-interstitial, just awkwardly squeezing between rows and distorting the whole lattice. But then, introduce a new concept, impurity atoms. This is where an entirely differently sized atom comes into play. It might substitute in for a native atom, or it might just wedge itself into one of those interstitial spaces. It really highlights the fundamental difference between an atom simply missing from the native structure versus deliberately shoving completely foreign impurity atoms into the mix.
You know, you might be wondering, just how common are these empty theater seats, these vacancies? Well, surprisingly, the fundamental laws of thermodynamics dictate that as temperature goes up, the number of defects absolutely has to increase. The heat is literally increasing the entropy, the randomness, of the crystal. To put that into perspective, if you heat most metals up to just below their melting point, roughly 1 out of every 10,000 lattice sites is completely empty. It's not some rare glitch. It is a guaranteed, mathematically predictable feature of the material.
Okay, let's jump into Section 3, impurities and solid solutions.
So what happens when we take the wheel and intentionally introduce foreign atoms to create something entirely new? Well, when creating these solid solutions, we use some specific terminology, kind of like you would in chemistry when mixing salt water, to differentiate the main material from the added impurity. The solvent, or the host atoms, refers to the element present in the greatest amount. That's your main structure. The solute, on the other hand, is the element present in a minor concentration. These are the impurity atoms we are purposely sprinkling in to hack the material's properties.
A perfect, everyday example of a solid solution is sterling silver.
If you tried making jewelry out of pure 100% silver, sure, it'd look pretty, but it'd be so incredibly soft that it would bend and scratch almost instantly under normal wear. But when you use sterling silver, where silver is the host atom at 92.5% and copper is the solute at 7.5%, you're adding a secret weapon. That tiny concentration of copper acts as an engineered defect, massively beefing up the mechanical strength so your ring doesn't get crushed, all while keeping that gorgeous corrosion resistance of the silver.
Right, moving on to section 4, the rules of substitution.
Now, here is the catch. Atoms can't just mix however they want. You can't just mash any two elements together and expect a nice, stable, solid solution. There are strict natural laws governing this, known as the Hume-Rothery rules. Think of these as the absolute VIP entry requirements for material science. They dictate whether solute atoms can smoothly substitute for host atoms without totally warping the structure and creating a completely different phase. First off, the atomic size difference between the two atoms has to be less than about 15%. If the guest is way too big or way too small, it disrupts the lattice entirely. Second, their native crystal structures absolutely have to match. Third, their electronegativities, which is how strongly they attract electrons, must be similar. Otherwise, they'll form a chemical compound instead of a solution. And finally, a metal prefers to dissolve another metal of a higher valency over one of a lower valency. The whole shebang has to align perfectly for a clean substitution.
But that raises a pretty obvious question, right? What happens if an impurity atom completely ignores that 15% size rule? If it's substantially smaller than the host atoms, it obviously can't substitute in and take a regular seat. So, how does it get into the party? Well, instead of substituting, they find the empty spaces. These tiny impurity atoms literally squeeze themselves into the interstitial voids, those microscopic empty gaps between the much larger host atoms. Depending on the exact geometry of the host crystal, these tiny gaps are called tetrahedral and octahedral sites. A classic real-world example of this is carbon and iron. A carbon atom is vastly smaller than an iron atom, so it can't substitute for iron. Instead, it wedges itself right into these specific interstitial voids. And get this, that exact interstitial impurity is what transforms regular basic iron into high-strength steel. Talk about a game changer.
And finally, let's wrap things up with section 5, calculating material composition. To ground all these visual concepts in reality, we have to distinguish between two crucial ways engineers actually evaluate these imperfect mixtures. First, we have weight percent. This is based on the physical mass or weight of an element relative to the total alloy weight. It's super practical because, frankly, it's easy to just measure out on a scale in the lab when you're physically manufacturing the alloy. But then we have atom percent. This one is based on the number of moles, or the actual count of atoms, relative to the total atoms in the alloy. This tells us the real ratio of atoms interacting at the microscopic level, which at the end of the day is what actually determines the physical properties we've been geeking out about.
Because 1 mole of any substance contains the exact same number of atoms, shout out to Avogadro's number, we rely on specific conversion equations to translate our physical mass measurements into that microscopic atomic reality. These formulas take the mass of the elements, combine them with their specific atomic weights, and output the precise atomic percentages. Without this math, engineers couldn't reliably calculate exactly how much solute to add to hit that perfect sweet spot of intentional imperfection.
So I want to leave you with a thought as we wrap up this explainer. Just take a look around the room you're sitting in right now. Look at your phone, the structural beams hidden in your building, the keys on your desk, maybe the car parked outside. Consider that the immense strength and everyday utility of the materials all around you rely entirely on the precise mathematical mastery of flaws. Perfect order might sound like an appealing idea in theory, but as it turns out, it's the engineered imperfections that are literally holding our modern world together. So how many powerful, engineered imperfections do you think are hiding in the things you rely on every single day? Thanks for joining me on this deep dive, and keep an eye out for the brilliant flaws all around you.